Okay, so thermo now. So last time we started talking about the first law for control volumes. So now we're talking about doing calculations for devices where some kind of fluid is flowing in one side and flowing out the other side. This fluid can be a liquid or a gas, or saturated, a mixture of the two. And the first law for control volumes is this sort of ugly looking thing that says dE dt inside the control volume is equal to Q dot for the control volume minus W dot for the control volume. So far everything looks familiar. And then there are two big terms that deal with the fact that fluid is flowing in and out. So the first one at the inlet is m dot at the inlet times the quantity, HI plus VI squared over 2 plus GZI. And remember last time I went through that derivation to show where we get that enthalpy from, and it's just a combination of things that end up being convenient to group together. But that specific enthalpy is equal to the specific internal energy plus the pressure times the specific volume. And then minus m dot at the exit times the quantity H at the exit plus V squared at the exit over 2 plus GZ at the exit. So there it is. That's the full form. And we're almost never going to use that full form. Maybe never. But the way I want you to go, get used to starting with that full form and then just think, why can I cancel this? Why can I cancel this? Okay. So I'm going to tell you some sort of standard simplifications, but even when you use these devices, the questions are going to vary what things you can set to 0, what things you can assume go away, that kind of stuff. Okay. So I want you to get in the habit of starting with this and then thinking, okay, why can I cancel Q dot for this? Why can I cancel? Okay. All right. So we're going to do this for 5 main devices right now. And those are nozzles and diffusers. Those sort of naturally go together because they're just kind of exactly opposite devices. Turbines. And then compressors and pumps. So I'm going to start with nozzles and diffusers, and we'll talk about why you can cancel the things that you can cancel. You can think of these two things as the same device with just fluid flow going the opposite direction. So for a nozzle, you're increasing the speed of the fluid and decreasing the pressure. So if this is the device, the flow of the fluid is this way. So this is the inlet side, this is the exit side on the right. At the inlet, you have high pressure and low speed. This speed, one thing to watch out for is we use capital V's in a couple of ways. We use it for volume, but for this, we're using it for speed. Okay. And then at the exit, the purpose of a nozzle, well, it does get the pressure down, but we tend to use it just to increase the speed. So you have a big exit velocity. And a diffuser is the exact opposite thing. So in this case, your inlet is this side, and your exit is this side. So you have the fluid flowing really fast. Well, you would need this fluid to be coming down a pipe or something. But you have a high speed at the inlet and a low pressure. And then at the exit, you have a low speed and a high pressure. Okay, so that's what we're trying to accomplish with this thing. That's why you put those in there. So now let's think about the assumptions. What kind of cancellations happen? And these are just the standard assumptions, but like I said, you're going to have to go problem by problem from the full form of the control volume first law. Okay, so first we're going to assume this is steady state. Do you remember what happens if something's in steady state? There are two things that happen. First, dE dt is 0. And second, the mass flow in has to equal the mass flow out. So instead of having a, m dot at the inlet and m dot at the exit, you can call them both just m dot. It's just the flow through the device. Second is we're going to assume that the change in potential energy is negligible. Okay, so in here, the potential energy terms are the GZs, so those we'll cancel those out. We'll ignore those. Third, we'll assume that this is relatively fast flow. And so if the material is spending a very small amount of time in the control volume, what can we cancel for that, because of that? Q. That's right, yep. So Q dot for the control volume is equal to 0. It just doesn't have time to transmit heat across the boundary. And then the fourth one, these are just rigid devices. They're made out of metal or plastic or whatever. And so there's not going to be any work of expansion. There's no spinning shafts. There's no electrical work being done. Everything's just rigid. And so W dot is also equal to 0. Okay, so let's go back to this full equation. So that's at the inlet, and then minus m dot at the exit times the quantity enthalpy at the exit plus V exit squared over 2 plus GZE. And let's start canceling stuff. So this goes away. These both, we'll just call them m dot. So those don't have to be different anymore. There's no heat transfer. There's no work. And there's no change in potential energy, so we'll cancel those two. And so the form that we end up with is HI plus VI squared over 2 is equal to HE plus VE squared over 2. Okay, so that's the final simplified form. That's sort of the standard simplified form. But you won't always use this exact form for nozzles and diffusers, but this is always the basic idea of what's happening. So let's think about what this means for the two of them. Even though it's the same equation for both of them, I'm going to organize these terms in different ways just to sort of bring out what these are trying to do. Okay, so for a nozzle, the exit speed is bigger than the inlet speed. So I'm going to organize this as HI minus HE is equal to VE squared over 2 minus VI squared over 2. Okay, so I have it organized so that both of these sides of the equation are positive. And then for a diffuser, I'm just going to get them over on the opposite sides. So for a diffuser, the speed is higher at the inlet, lower at the exit. So I'm going to write this as VI squared over 2 minus VE squared over 2 is equal to the enthalpy at the exit minus the enthalpy at the inlet. And again, for a diffuser, these are both positive. Okay, so what are we doing in a diffuser or in a nozzle? In both of these, we're exchanging enthalpy for speed, okay? Any questions about that? Okay, let me do an example. So let's say that steam enters a nozzle. at a pressure of 10 bar, and a temperature at the inlet of 400 degrees Celsius. And it leaves at a pressure P2 of 3 bar. Well, I call this P exit. And a temperature at the exit of 200 degrees Celsius. If the speed at the inlet is 20 meters per second, what's the final speed? Okay, well, we're starting with a superheated vapor. How many properties do you need to know the other properties in a superheated state? 2, right, and we have them, pressure and temperature. The fact that the properties are pressure and temperature makes right away, it should just jump to your mind that like maybe this is a thing where we're going to use a table, okay? Because that's how our tables are organized, pressure and temperature. I mean, they could be organized with any 2 properties, you know, and you can use them that way, but you have to do a sort of painful reverse lookup thing. It's not the most pleasant thing. Okay, it doesn't say that it's steam at the exit. Is that going to be steam at the exit? I think probably that's about 3 times. So I'm thinking that this is steam in both of these 2 cases. And we have tables for steam. So, you know, for water, we have water tables. So we can look all this stuff up in tables. This doesn't give us any information about what to cancel, you know? And so in this case, we're just going to use our best guess and use the standard stuff for the for diffusers and nozzles. So we could jump right to this equation, but let's just go through the process again of just canceling them out quick. Personally, I think it's good practice just to write down that complicated equation a bunch, make it stick in your head a little bit. Okay, so we got dE dt for the control volume is equal to Q dot minus W dot plus MI dot times the quantity HI plus VI squared over 2 plus GZI minus ME dot times the quantity HE plus VE squared over 2 plus GZE. And now we'll start canceling stuff. That's gone, 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 gone. And those are both the same. So we can write this as HI plus VI squared over 2 is equal to HE plus VE squared over 2. Now we're going to look up, so what do we need to look up? We're given this, okay? We're trying to find VE. We have properties that'll let us look up the specific enthalpies at the inlet and the exit. So look up H inlet and H exit, and what you get is at the inlet, the enthalpy is 3263.9 kilojoules per kilogram is how they give it in the table. We're going to do this in SI units, so I'm going to write this as times 10 to the third joules per kilogram. And then at the exit, we got 2865.5 times 10 to the third joules per kilogram. Okay, one thing about units with the control volume equation. Up until now, I've always been using SI units pretty much. But you can use a lot of different types of units for the different things. But for this control volume first law, I think you probably always want to do it in SI units because your speed is going to be in meters per second. And if you're using kilojoules and then you're using SI units for the speeds or for the potential energies, everything's out of whack. Okay. Okay, so our equation simplifies to, so the speed at the exit that we're trying to calculate squared over 2 minus the speed at the inlet squared over 2 is equal to 3263.9 times 10 to the third minus 2865.5 times 10 to the third. And so VE squared is equal to 400 plus 2 times the quantity 3263.9 times 10 to the third minus 2865.5 times 10 to the third. Square root of both sides, and you get VE is equal to 892.9 meters per second. And don't put your hand in front of superheated steam at 892 meters per second.
When I was like 17, 16 years old and my car was overheating,
Uh-huh.
my dumbass not
Oh, yeah.
doing just pop cap right off the radiator cap.
Uh-huh.
And somebody was watching over me because it was empty. And
Oh.
like, it just, nothing happened.
Oh, yeah.
No, until many, many years
Yeah.
later, I was like, that was not smart.
Yeah. Yeah.
I could have really, really burned myself real
Yeah.
bad. Yeah.
Yeah, like in the kitchen or whatever, you pretty much never see superheated steam. You only see saturated steam. And so you think of steam as visible, because it's visible because it's condensing, bits of it are condensing, but because it's at saturation and as it loses energy, some of it's going back into liquid form. Yeah, if you do a two-stage thing where you heat it up to saturated steam and then you heat it up from there farther, you have an invisible thing that does a lot of damage to human tissue. You can do it in your kitchen, but you should be careful. Any questions about the process? Okay. So the next thing is turbines. And I'm going to try to draw this. So I'm drawing sort of a cross section of the pipes that are leading to a turbine. And so here's the inlet. Here's the exit. So this is all just the pipe. And in here, you have your turbine blades. And these are connected to each other. By a shaft. And so the fluid flows, forget that. Okay, so the fluid flows this way and this way. And we have a high pressure at the inlet. And a low pressure at the exit. And that pressure difference is what forces this time it's a gas. It's rarely a liquid. The pressure difference is what forces the gas through and turns these turbines. And turning those turbine blades does one of two things. It either physically rotates a shaft, or it's used with electricity and magnetism to power a motor that sends out electrical work. So either way, you're getting work out of it. You know, it's mechanical work for the shafts, or it's electrical work through the motor, from the motor. The assumptions that, so these are like the standard assumptions that we're going to make. Again, you should always start with the full equation. But this just gives you kind of an intuitive idea of what a turbine is doing. First, we're going to assume steady state. And so that does the same two things that it did for nozzles and diffusers. dE dt is equal to 0. And m dot at the inlet is equal to m dot at the exit is equal to just, we'll call it m dot. Second, we'll assume that the change in potential energy is negligible. Third, we're going to assume that the change in kinetic energy is negligible, even though I was going to say that the fluid slows down, but actually it doesn't slow down. I think in a lot of cases it speeds up because of that pressure difference. But anyways, you saw in the last case, if you're not dealing with very, very high speed gases, the contribution of kinetic energy is so small compared to the contribution of pressures, enthalpies, stuff like that. Like, look at this pathetic, sad little term of 400 from that 20 meter per second gas, you know? So we're going to assume that this doesn't do much. And then this is fast. And so we're going to assume that no heat is transferred. Okay, so start with the full equation. dE dt is equal to Q dot minus W dot plus MI dot times the quantity HI plus VI squared over 2 plus GZI minus ME dot times the quantity HE plus VE squared over 2 plus GZE. And dE dt is 0. MI dot is equal to ME dot, so those are just M dots. There's no heat transfer. There is work, because we're either getting electricity or mechanical work out of this thing. And we're canceling kinetic and potential. And so what you get out of this is, let me see what form I put this in before. I guess let's put it into W dot for the control volume is equal to M dot times the quantity enthalpy at the inlet minus enthalpy at the exit. And this form that I have it in, both sides of this equation are positive. Because with our sign convention for the first law, positive work means that work is being done on the surroundings. Okay, not the surroundings doing work on the, so this is outputting either electrical work or mechanical work. And it's doing it through a decrease in enthalpy as the gas goes through the device. Okay. Later in the class, when we talk about like power plants and stuff, and we talk about power generation cycles like more realistically, we'll talk about some of the concerns here, like for example, practical concerns. As you lose enthalpy, it's very easy to go from a superheated vapor to a saturated state where you start to get condensation, and that condensation is very, very hard on turbine blades. And so there are all these strategies that people use to make sure that you have superheated vapor in both cases. And then there are also some benefits to, rather than using superheated vapor, to get the temperature and pressure up above that critical pressure and temperature, where you have a what do they call it? A supercritical fluid. There are some benefits to that. Mostly the very high pressure gives you more efficiency, but then you have this fluid that can also do a lot of damage to things. And so we'll talk about that kind of stuff later. But for now, we'll assume that the machinery can just handle anything we throw at it. Okay, so here's an example with a turbine. So let's say that we have steam. So we mean superheated steam. And the mass flow rate is 1.2 kilograms per second. And at the inlet, we have an inlet pressure of 60 bar, an inlet temperature of 400 degrees Celsius, an inlet speed of 10 meters per second, And then at the exit, we have an exit pressure of 0.1 bar. A speed of 30 meters per second, and a quality of 0.9. Okay, so what does it tell us that at the exit, we're given a quality?
Saturated.
Yeah, that's right. It means that it's saturated because what that quality tells us is the fraction that's vapor and the fraction that's liquid. Okay, and so so given all this stuff, since we know that it's steam at the inlet, we have a pressure and a temperature. That's enough for us to look up values in the table. Okay, so you're thinking table for this. And then in the second case, well, we're only given a pressure at the exit, but since we're given a quality, we know it's saturated. So we know we can use a table for this too. We have everything we need to look up anything we want in the table. And enthalpy's in there, so that's good. That's what we would want to look up. So first, we're going to use the standard assumptions for a turbine. And we're going to find the power generated. And that's what this is. Work dot is the power. Second, we're going to calculate the error that we got in assuming that kinetic energy is balanced, because we're given speeds at both cases. So we can actually calculate that kinetic energy difference. So what's the error in assuming our change in kinetic energy is equal to 0? And then third, now we're going to remove the assumption that Q dot is equal to 0. And we're going to assume 1,000 kilowatts of power output. What's the rate of heat loss? Okay, so first we're going to use the simplified equation that we got before that says the power, W dot, is equal to M dot times the quantity H inlet minus H exit. We're just going to look up. So in a steam table, we're going to look up that H at the inlet is equal to 3658.4 times 10 to the third. This would be watts per kilogram. Oh no, not watts. This is not a time derivative, so this is just joules per kilogram. And now we'll go to the saturation table. And it tells us that the enthalpy for the saturated liquid at that pressure that's given is 191.83 times 10 to the third joules per kilogram. And the same line in the saturation table also tells us that the enthalpy for the gas at saturation is 2584.7 times 10 to the 3 joules per kilogram. Okay, so now how do we use those to calculate the specific enthalpy for the whole combination of liquid and gas?
Quality?
Yeah, we have that quality equation, so we know that H at the exit is going to be the quality times H for the gas plus 1 minus the quality times H for the liquid. So that's 0.9 times 2584.7 times 10 to the third plus 0.1 times 191.83 times 10 to the third. And you get a total specific enthalpy at the exit of 2345.4 times 10 to the 3 joules per kilogram. So now that we have the two enthalpies, we can go to this simplified equation, and we have that work dot for the control volume is equal to the mass flow rate, which we were told in this problem is 1.2 kilograms per second. Again, notice I'm putting everything in SI units for this. So 1.2 times the quantity, 3658.4 times 10 to the third, minus 2345.4 times 10 to the third. And you get a power output of 1575.6 times 10 to the third. This is joules per second or watts. Okay. Well, to use that simplified form, we assumed that kinetic energy didn't change. So what's the change in kinetic energy? We're going to see that it's really small. So the change in kinetic energy and this actually would be, how did I write that? So what it really is the time derivative of the change in kinetic energy. But this is equal to 1/2 times the mass flow rate times the quantity, V at the exit squared minus V at the inlet squared. And you can just plug in the speeds that are given, and this gives negative 480 joules per second. So if you look at the order of magnitude that we have for our power generation, it was very reasonable to just ignore this. You see why we tend to set that equal to 0. And then the last thing that we're calculating. Okay, so now for C, we're not going to assume that it's insulated and fast and that there's no heat transfer. We're going to let the heat transfer stay in the equation. But we are going to make an assumption about the power generation. Okay, so we're assuming 1,000 kilowatts of energy output. So let's go back to the full equation first of all and see how the heat transfer it appears in the equation. So we have dE dt is equal to Q dot minus W dot plus, none of this stuff is gonna change, so I'm just gonna leave this as M dot times H inlet minus H exit. That goes away, and we get that W dot for the control volume is equal to Q dot for the control volume plus M dot times the quantity HI minus HE. We're assuming 1,000 kilowatts of work production, so that's 1,000 times 10 to the third watts is equal to Q dot for the control volume, plus this stuff that we just calculated. So 1575.6 times 10 to the third. And right. Work is equal to what did we have at the inlet here? Okay, we got the big one at the inlet and the small one at the exit. Oh, yeah. Okay, so, right. So subtract 1575.6 from both sides, and you get negative 575.6 times 10 to the third is equal to Q dot for the control volume. So our answer is CV dot is equal to negative 575.6 times 10 to the third, and this is in watts. And now, does it make sense that the sign is negative? Yeah, think about the sign convention for the first law. Q is positive if heat is coming into your system. Our system is losing heat to the surroundings, so that has to be negative. Any questions about that? Okay, well, we'll finish with this on Wednesday with compressors and pumps, and I'll give you a couple problems to work on before then.